Good morning. This class we discuss Thomson method to find charge to mass ratio of electron. We can use Thomson method to find E by m of an electron, and in this class we will be discussing the theory of Thomson experiment to determine the charge to mass ratio of electron. What in the experiment what we will do is we will apply both electric and magnetic fields to a beam of electrons ejected from an electron gun. Then in the presence of electric field it will be having deflection in one direction. Let us take the deflection of electric field is along the positive y direction. We are applying electric field between two plates. That plates are kept in the horizontal direction, and the field upper plate, if I give upper plate positive charge and lower plate negative charge, then we will be having an electric field in the downward direction. If electron is moving perpendicular to that electric field, the electron will be deflected in the vertically upward direction. So in the presence of electric field, we are getting a deflection in positive y direction. Now we apply a magnetic field perpendicular to both the direction of motion of electron and direction of electric field. So it is moving along this x direction, and electric field is applied in the negative y direction, and I am giving a magnetic field in the z direction. So in the presence of magnetic field, the electron will experience a force, and I will align the magnetic field, the direction of magnetic field in such a way that the shift due to magnetic field is opposite to the shift due to electric field. If both the shifts are same, then we will be having an undeflected beam at the screen. So this is the experiment we are going to perform. We are applying both electric and magnetic field. The case with the electric and magnetic fields we will be discussing separately. When we take the combined fields, there may be a slight change in path, but we are not taking that small change. That can also cause an error in this experiment. We are treating them separately. First, I will take the case with the electric field. Let us draw the diagram. Consider a beam of electrons which is emitted from so this is several anodes are used for accelerating the beam. So I am taking this as one anode, last anode. So before that we are having several anodes, and from this anode the electron beam is ejecting, and I am drawing the electron beam ejecting along this direction. The electron beam is moving. The undeflected beam will be moving. The undeflected beam will be moving like this. In the absence of both electric and magnetic field, we will be having a beam like this. In the presence of this is screen. So this is screen. In the presence of electric field, we are applying electric field along the downward direction. So these are the plates for applying electric field, and we are applying electric field along the downward direction. Let L be the length of this plate and capital L be the distance from the end of this plate to screen. This is screen. And this total distance I am taking it as P. This is last anode. This one is last anode. We are having several anodes here. Then electron gun is situated somewhere here. From that, electrons are ejecting, and this is accelerated towards the anode. The anodes are having slight slits. So through that slit, the electron beam is ejecting outwards. So when I apply electric field, this is positively charged plate, and the lower sheet I have given negative charge. So an electric field is applied in the negative y direction. So we are applying an electric field in downward direction. Since the electric field is in the downward direction, the electron will be having an acceleration positive y direction. So this is y direction, and this direction I'm taking this as x direction. So this electron will be deflected in the positive y direction. So when it ejects out of this plate, there is no electric field. So if it is having a velocity tangent to this path like this, then after that it will move. After that it will move undeflected. So from here to from here it will be moving along a straight line path. So this it will be moving along a straight line path. From here to here it will be moving in the presence of electric field. The electron will be moving along a parabolic path. So from here to here the electron beam will be moving along a parabolic path, and after that it will be moving along a straight line path. So this shift I am taking it as y1. Then this shift I am taking it as y2. So the total shift of beam will be y1 plus y2. Total shift of beam, shift y is equal to y1 plus y2. So in electric field, first we are calculating the presence of electric field. Presence of, this is figure 1. Figure 1 represents the presence of electric field. The presence of electric field. Let V be the velocity with which the electrons are ejecting out of the last anode. Let V be the velocity with which the electrons are ejecting out of the last anode. E be the electric field applied along the negative y direction. If V is the potential difference between the plates and D is the separation between the plates separation between the plates. Then electric field E is equal to V by D. Electric field E equal to V by D. Now the acceleration, electron will be accelerated in the positive y direction. Electric field is along negative y direction, so the electron will be accelerated along the positive y direction. The acceleration, the magnitude of acceleration along positive y direction, positive y direction, y ay, that we can take it as ay. So ay equal to force is QE. Here electronic charge is E. Magnitude we are taking, which is along positive y direction. So E by m, force by mass, we will get the acceleration. Then what will be the shift when it ejects out of the electric field E? When it ejects out of the electric field E, it is traveling a distance L along the horizontal direction and y1 along the y direction. So when the electron comes out of the plates, it will travel a distance L along horizontal direction and y1 along vertical direction. Therefore, the displacement y1 equal to, we have the expression S is equal to uyt plus half ayt square. So displacement is y1 equal to initial velocity along y direction is 0. Then S is equal to y1. Ay is E by m. So this equation is first term becomes 0, half, what is Ay? E by m into t square. Now for finding t, take the horizontal direction. Horizontal direction, it is undergoing uniform motion. So along the horizontal direction, this is along vertical direction. Vertical direction. Along the horizontal direction, it is undergoing uniform motion. So the expression is S is equal to Vt. So horizontal displacement L is equal to horizontal velocity is V, which is the velocity with which the electron ejects out of the last anode. Then V into time taken is T. So T we can write it as V by L. Then the above equation becomes, therefore y1 equal to half E by m. This is, sorry, it is L by V. T equal to, not V by L, this is L by V. T is equal to L by V. So this is L by V the whole square. So we can write this equation as y1 as y1 equal to E L square by 2mv square. This is expression number 1. So we got the vertical displacement when it comes out of the sheet. Now after that it is moving along a straight line. Let theta be the angle made by the electron beam when it comes out of the sheet. When it comes out of this plates, it is having a deflection theta with horizontal, that deflection remains constant. So from figure we can write tan theta. Tan theta is y2 by this distance. This distance is taken as capital L. So tan theta equal to y2 by L, or y2 we can take it as y2 equal to L into tan theta. So if theta is the deflection of electron beam when it comes out of the plates, then y2 equal to L tan theta, where L is distance from end of plates to screen. So y2 equal to L tan theta. Now we need to calculate tan theta. When it ejects out of this plate, it is having a horizontal component of velocity and vertical component of velocity. The horizontal velocity remains constant. What will be the horizontal velocity? There is no force along horizontal direction. So horizontal velocity will be v. Now we need to calculate the vertical velocity. So we are having velocity v. We are having velocity v along this direction. This will be having a horizontal component. This will be having a horizontal component and a vertical component. Now this is velocity v, this angle is theta, and its horizontal component vx is same as, sorry, this is not v, I am taking it as v prime, velocity with which it is ejecting out of the plate, that is I have taken it as v prime, and the horizontal velocity will be same as the velocity with which it is ejecting out of the last anode. Since there is no force along the horizontal direction, horizontal velocity remains constant. This velocity I am taking it as Vy. Now what is Vy? Velocity along the vertical direction. Velocity along the vertical direction you can write using the equation of motion V equal to U plus At. Vy equal to Uy plus Ay into T. So Vy equal to, what is Uy? Initial vertical velocity is 0. What is Ay? Ay is E by m into T. What is T? T is L by V. So this is Vy. Now from figure find tan theta. This I am taking it as figure 2. From figure 2, tan theta equal to Vy by Vx equal to EEL by MV divided by V. So this will be tan theta equal to EEL by MV square. Now what about Y2? Y2 equal to, what is Y2? Y2 equal to L tan theta. So this equation becomes Y2 equal to L into tan theta, EEL by MV square. This is equation number 2. So once you know y1 and y2, the total shift along vertical direction, total shift along vertical direction, y equal to y1 plus y2. So y equal to, what is y1? Y1 is EEL square by 2mv square. EEL square by 2mv square plus, what is y2? Y2 is LEEL by MV square. From both these terms, I am taking EEL by mv square common. So this will be y equal to EEL by mv square. When I take by EEL by mv square, here will be having L by 2 plus EEL by mv square will be having L. So our expression for vertical shift in electric field is y equal to EEL by mv square into L plus L by. Using this expression for electric field, we cannot calculate the value of E by M. Why? We know the electric field, then we know the L, value of L, but V, velocity, we don't know the velocity with which it is ejected from the last anode. So we will apply magnetic field, and using electric and expressions for electric and magnetic field, we can simplify it. Now, what is the value of electric field intensity E in terms of potential difference? It is V by D. So we can write Y as EVL by DMV square into L plus L by 2. This is equation 4 and this equation I am taking. Since instead of electric field, we are knowing the value of potential difference V. So using this equation, we can calculate the shift, calculate the E by M provided V is known. Since V is not known, we will take the case with the magnetic field. Now we apply a non-uniform magnetic field. So the CRT cathode ray tube is like this. Electron beam is ejecting and it is incident on the screen. We will be having a white spot here. And then we have given electric field between these two plates. So this will be deflected in the positive y direction, and that deflection is cancelled by applying magnetic field along the perpendicular direction. Along this direction, I will be applying a magnetic field. Electric field is applied along this direction. The electron beams are moving along this direction. So the electric field will be balanced by magnetic field. So the electron beam, in presence of electric field, the electron beam is shifting in the positive y direction. So you apply magnetic field along the z direction, positive z direction or negative z direction. You select the direction in such a way that the shift of electron will be in negative y direction. If shift due to electric field is equal to shift due to magnetic field, then you will be having an undeflected beam here. So, in the experiment, what you are doing is you first you will be applying a magnetic field and you will find the shift for that. Then you will apply an electric field and vary that electric field such that this shift becomes zero. Since you are getting undeflected beam, that means the shift due to electric field Y balances the shift due to magnetic field. If shift due to electric field is along positive direction, shift due to magnetic field will be along negative. If shift due to electric field is along positive Y direction, shift due to magnetic field will be along negative Y direction. Now we will apply magnetic. For applying magnetic field, we will be keeping a bar magnet here, then here also equidistant we are arranging a bar magnet. Now effect of next page we will discuss the effect of non-uniform magnetic field B. So here we are giving a bar magnet. So we are providing a non-uniform magnetic field along the path of electron beam. So this is the direction of motion, x direction. This is the direction of motion, and electric field is along the y direction, and I am applying magnetic field along a perpendicular direction. Magnetic field is applied along this direction, and here I am keeping a bar magnet. See, electric field is applied in negative y direction, so electric field will provide a force in the force due to electric field. Force due to electric field is along the force due to electric field is along the positive y direction. Now it will experience a force due to magnetic field in negative y direction. For obtaining force due to magnetic field in negative y direction, the expression for force is F is equal to minus E V cross B. Actually, it is Q V cross B. Magnitude of force is magnitude of magnetic force is F equal to E VB sin theta if V and B are perpendicular. If E if V and B are perpendicular, then it will be minus EVB. Magnitude of force will be EVB, which should be along the negative y direction. So for making F along the negative y direction, here already one negative sign is there. So V cross B should be along the, actually the expression for force is F is equal to QV cross B. For positively charged particle, force is along the direction of V cross B. For negatively charged particle, force is along the force is opposite to the direction of V cross B. So here electrons are moving, so its magnetic force should be opposite to V cross B. Now see the direction of V cross B. If I apply magnetic field along this direction, if I am applying magnetic field along this direction, and V is along this direction. Now, what about V cross B? B is into the plane and V is along this direction. So V cross B will be in the upward direction. So if V cross B is in the upward direction, then the minus V cross B will be in the downward direction. So the electron will shift in the downward direction. For that you should apply. So here you should be having north pole, and here you are having south pole, and here south pole, then here north pole. Then this magnetic field will be along this direction. So this will be along, this will be into the plane. We are applying magnetic field, direction of magnetic field is into the plane. Then you will be having V cross B in the upward direction, minus V cross B will be in the downward direction. So magnetic force effect of non-uniform magnetic field. So in magnetic field, if B is the magnetic field intensity at a distance x, then the magnitude of magnetic force F is equal to EVB. We are taking magnitude, so it will be EVB, since V and B are perpendicular. V and B should be always perpendicular. If I draw the z direction along this and x direction like this, and I am keeping magnet here it is north and south pole. Here we are having south and north pole, and magnetic field is at this point, the magnetic field is along this direction. So when I take a point somewhere here, the velocity of electron is along x direction. This is x direction, and upward direction I am taking y. Magnetic field is applied along the negative z direction. This is x direction, and the vertical direction I am taking it as y. Then out of plane will be z direction. This magnetic field will be z direction will be This is Z direction. So the magnetic field is applied along the negative Z direction. So this this direction I am taking Z direction. This is X and upward direction out of plane. I have rotated the coordinates. So this is negative Z direction. Field is applied along negative Z direction. See a point somewhere here. If I take a point somewhere here, then the magnetic field lines from these two magnets will be like this. So at this point, the magnetic field, direction of magnetic field and velocity are perpendicular. Consider a point somewhere here. Here also, since you are using two magnets symmetrically on the two sides, always along the path, the magnetic field and velocity vectors are perpendicular. So V and B are always if I take only one magnet, then it is not perpendicular. Since you are keeping two magnets symmetrically on both sides, always, since we are using two magnets symmetrically the B is the direction of the B and V are always perpendicular along the path. So V and B are always perpendicular. Since V and B are perpendicular, so no harm for taking the magnitude of magnetic forces EVB. Otherwise, you need to take EV cross B. So magnetic force is EVB. The effect of magnetic field is to rotate the particle. The effect of magnetic field is to rotate the electron. So the centripetal force mv square by r, that will be equal to the magnitude of magnetic force. Magnitude of magnetic force is ev. Magnitude of magnetic force is evb. So from that we can calculate the expression for r as 1 by r equal to eb by mv. 1 by r equal to ev by mv. Now the expression for radius of curvature of a path, here we are having anode. From anode the electrons are rejected, and this is this. Sorry. So this is the screen, and this one is anode. From here the electrons are rejected, and in the presence of magnetic field, instead of going straight, it will be deflected. We are arranging magnetic field in such a way that it is deflected in the negative y direction. So this magnetic field, the shift in magnetic field should be same as the shift in electric field. That's why when you apply both electric and magnetic fields, then we will be getting undeflected beam. So this is velocity v. So when I take a path somewhere here, the radius of curvature of this path, this will be like this. The radius of curvature of this path is given by 1 by r equal to d square y by dx square by 1 plus dy by dx the whole square, the whole raised to 3 by 2. This is the expression for a radius of curvature. If dy by dx is very small compared to 1, if dy by dx is very less than 1, we can write 1 by r approximately equal to d square y by dx square. So this 1 by r I can take it as d square y by dx square equal to eb by mv. So this is eb by mv. Now on integrating this equation I am taking it as this equation number equation 4. Now this is 4. So this equation I am taking it as equation 5. On integrating equation 5. When you integrate equation 5, you will be having dy by dx equal to e by mv is constant. So I can write e by mv into integral b dx. So this is equation 6. On integrating equation 6, for finding y, you need to integrate. Y is total shift, so you need to integrate along the total length. This total length is given as p, so you need to integrate from 0 to p. So on integrating equation 6 from 0 to p, then we will be having y is equal to total shift y equal to e by mv is constant. Then integrate the function integral b dx. So integrate this from 0 to p. So we will be having a double integral like this. I am writing this integral as ei by mv. Equation number, this is equation 7 and this one is equation 8, where the double integral I equal to integral 0 to p integral b dx equation 8. So if you know this double integral, then I can give this value in the above equation. From equation 8 we can calculate the expression for v. From equation 8 v equal to, what is v from equation 8? V equal to, from this equation, v equal to ei by my. Therefore equation in the electric field expression for y is equation 4. Therefore equation 4 becomes we are taking the shift in electric field balances the shift due to magnetic field. That's why both the shifts we are taking it as same. So equation 4 becomes y is equal to ev EVL by dmv square. E capital V L Y dmv square. Instead of v square, I can write square of this one. So this is E square I square by m square y square into L plus L by 2. This E by m. One E by m will cancel with this one. Then this y square, simplifying this, we will be having y equal to this E by m I can take to left hand side. This y square will come in numerator and that one y will cancel with this y. This E by m I am taking to left hand side. So I can write it as E by m. One E by m will cancel with this one. Then we will be having one E by m. That E by M I am taking to left hand side. So left hand side we are having E by M. Now this y square will go in numerator. That y square, one y will cancel with this y. So here y will cancel. Then numerator we will be having y. Then this m, y, v, l, m, y, v, l, m by I square into L plus L by 2. One D is there. D I square. Is it correct? E V, sorry, E by M equal to Y V L. Oh, sorry, this M is taken to left hand side. One M will cancel with it. So no M is there. E by M is taken to left hand side, then Y will get cancelled. Here we will be having this Y in the numerator. So Y V L by D I square into L plus L by 2. Y V L by D I square into L plus. So using this equation, we can find the value of E by M. Equation number, we can give equation number 9. So this equation I am giving. Using equation 9, using equation 9, by knowing the value of shift y, you can directly detect the shift y from experiment. Then this VL capital L, this electric field potential difference V, you can measure directly the potential difference V. Then this L D are constants. They will be given along with the instrument. So these are constants. We are not varying their values. So they are constants. So that constants are already known. So L, D are known. Then you need to calculate Y, V and I. Y, V you can directly measure, and the value of double integral I, we can calculate E by M. So we can calculate E by M provided these two Y and V we can measure by experiment. Now you need to calculate the double integral I. Now we see how to calculate the double integral. Evaluation of double integral I. How can we evaluate the double integral I? There are different ways to evaluate the double integral I. Here I will use a tricky way to evaluate the double integral. What I will do is, see the double integral I is equal to integral b dx, then integrating this from 0 to p. So this is our double integral. Now let us take this equation. I am giving this equation number 10. Now let us assume another function. Let a function, we are taking a new function. Let us give its name g. Let a function g equal to integral b dx. I am taking a function g which is integral b dx. Then what is dg by dx? Dg by dx will be equal to b. Now take this integral. Equation 10 becomes I equal to integral 0 to p. Instead of integral b dx, I am giving g into dx. This integral 0 to p, this I am writing it as g into 1 into dx. There is no harm in writing like that. Now we will integrate this by parts. Integrating by parts. So by integrating by parts, first function is g into integral of second function, integral of second function, integral 1 dx will be x. So this is gx, limit 0 to p, minus integral 0 to p, differential of first function is dg by dx into integral of second function is x dx. What about this gp? G at p into x, value of x is p. So g is integral b dx. So this will be integral 0 to p b dx into p, minus g at 0 into value of x is 0. Value of x equal to 0. That means at 0 this gx becomes 0. So minus this term will be 0. So second term will be 0. This one gx at p will be integral b dx p, then minus gx at 0 will be 0. Now this minus sign, minus of integral 0 to p, what is dg by dx? Dg by dx is b. So this is bx dx. This equation I can write it as integral 0 to p bp dx minus bx dx, or I can write it as b into p minus x dx. So this double integral I can write in the form, this is equation 12 and this one is equation 13. Equation 13. So using that equation, if you want, you can directly calculate from this equation. You find b into p minus x, then draw a graph between b into p minus x along y direction and x along x direction. Then you will be getting a graph something like that. Then this strip, area of this strip will be b into p minus x into x. Then integrate from 0 to p, you will be having total area. By finding that, you can evaluate this level. But the problem with that is, if you have an error in measurement of this area, then when you calculate, this error will be very large. So don't do direct calculation from this equation. Instead of evaluating using this graph, I will use another method for finding this integral 0 to p b into p minus x dx. For that, we will assume that the magnetic field at a distance x has, let us assume, so we are not going to take this one. Let us assume, since the error is large. So when you do like this, its error will be large. So instead of that, we will assume, let us assume the magnetic field at distance x is equal to this b, which is a function of x, that is equal to the average value of b plus error of b from bx, that I am taking it as x. Actually, x represents the error in magnetic field, the change in magnetic field, or hx equal to bx minus b bar, where where b bar is the average value of magnetic field from where to where, 0 to p, and h represents the variation of magnetic field. So this equation 13 becomes equation 13 becomes I equal to integral 0 to p. Instead of b, I am writing b bar plus h into p minus x dx. Is it right? b b bar plus h into p minus x dx. I am splitting into two terms, b into p minus x dx. Another term is h into p minus x dx. So if I split into two terms, integral 0 to p, integral 0 to p, b bar plus h into p minus, sorry, I'm splitting into two terms, b bar into b bar into b bar into b bar into p minus x dx. First term is b bar into p minus x dx plus, so b bar into p minus x dx plus integral 0 to p h into p minus x dx. What is b bar into p minus x dx? This b bar is constant. It is average value. So this is constant. So when I take outside b bar into integral 0 to p minus x dx plus this one is 0 to p h into p minus x dx. This b bar into p minus p is constant. So I can write it. This is first integral p into dx. So this term will be px minus integral of x will be x square by 2. Then integration limit is from 0 to p plus integral 0 to p h into p minus x dx. So this I can write it as b bar into, what is its value? P into p minus p. So p square minus p square by 2. This will be p square by 2. So b bar p square by 2 plus integral 0 to p h into p minus x dx. So this equation, this integral, I have evaluated the integral as this equation 16. Now see this equation, this is a constant value. With that we are adding this h is very small compared to b bar, which represents the variation from b. So this integral you can calculate using the area under the curve. This integral, the second integral, I equal to b bar p square by 2 plus this I am taking it as I1. This I1 integral where I1 equal to integral 0 to p h into p minus x dx, which can be calculated using the h into p minus x versus x graph. How can we calculate that? This will be given by the area under the graph. See that graph? So if you draw this graph, if you this is 0 and this is p, let this point be p, this is x, and y direction you are plotting h into p minus x. H into p minus x is along taken along y direction and x is taken along the x direction. If we are having this graph something like this, then if you take a strip of thickness dx, this is dx, then this height will be h into p minus x. So its area of strip, area will be, area of this strip will be equal to h into p minus x dx. Then the total area, integrate from 0 to, integrate this from 0 to p, then you will get the total area. Integrate this from 0 to p. So the integral I1 equal to integral 0 to p h into p minus x dx will be equal to area under the curve, area under the curve. So using that we can calculate I1. Once you know I1, then you can calculate I using this equation. So this is equation number 17 and this one is equation number 18. Equation number 18. So if you know I1, for finding I1, find the area under this curve. Then if you know I1, then find the value of I using equation 17. If you know the value of I, then you can calculate E by M using this equation. Here all other parameters. You measure Y, then V from the experiment, then find the magnetic field at different points. Using that magnetic field, you can do the following calculations and find the value of I. You can calculate the charge to mass ratio. So the observation column for doing this will be observation. Observation for doing this will be, we can have an observation column for this as you will be having first you are having first you will be having distance x. So first observation column you are having distance x, then find p minus x. P is total length, p may be 16 or something like that. P, if p equal to 16 centimeter, then find x will be, we will take from 0 to 4 etc. Then find the value of p minus x. Then you need the value magnetic field. For measuring the magnetic field, you need to measure the deflection in tangent galvanometer. Using tangent galvanometer, find the magnetic field at different x values, and using that you can calculate the, from deflection you can calculate the magnetic field. So these are for deflection. Deflection, deflection, then here it is theta 1, theta 2, deflection in tangent galvanometer, deflection in compass box. So theta 1, theta 2, then mean theta, then using that we can calculate B equal to BH tan theta. Using that equation you can find magnetic field using compass box. Then you have B, then find the value. Once you get B, then find mean B, mean B, that will be B bar, that is equal to mean B. Then H equal to, what is H? Value of H equal to B minus B bar. Then find B minus B bar. Next column, you will be finding H equal to B minus B bar. Then if you know H, then for drawing this graph, you need H into P minus X. So here you calculate H into P minus X. Then you draw graph. So using these observations, you can find, using these observations, you can find the value of E by M. So next class we will discuss how to do the experiment, and this class we discuss the theory behind the calculation of E by M using Thomson method. Thank you.